Why is the gradient the direction of steepest ascent? It's a fundamental tool in machine learning, but the geometric reason is often brushed aside. To see why, let's start at the beginning. In machine learning, we minimize loss functions with the input dimensions as adjustable parameters called weights. Our goal is to find out the weights that sit at the very bottom of these valleys where the loss or error is minimized. To get there, we use gradient descent. By taking steps proportional to the negative gradient at every point, we are guided downhill. But why is the gradient mathematically guaranteed to give us the steepest ascent at that point? To understand that, we need to understand derivatives. Specifically, loss functions are multivariable functions with thousands of input or weight dimensions. Here, for simplicity, we have only shown two, x and y. Suppose we want to find out the rate of change of this function in some arbitrary direction u. Now, the derivative of this function would depend on the direction in which you're taking the derivative, which is u. So we model this by defining a straight path r of t equals p plus t of u, where x and y have been parameterized by t. Now, we take the derivative of this function with respect to time, and using the chain rule definition, we get this directional derivative. Let's unpack this definition carefully. Does this look familiar from somewhere? If we pull the partial derivatives into a row vector and the directional components into a column vector, we get a matrix multiplication. And this is the dot product. This can also be written as the projection length given by del of f mod u mod times cos theta. But why is the multivariable chain rule giving us the projection lengths of these two vectors? To understand this, we need to understand the geometry of dot products. Think of some random linear transformation that collapses 2D space onto a 1D line. This transformation is entirely determined by where the basis vectors land. Let's say that the I hat lands on a sub I and j hat lands on a sub j. Then some arbitrary vector v in that 2D dimensional space would land on the point a sub I times v of x plus a sub j times v of y. Now, what if we are projecting this onto some random vector u? What would be the 2-to-1 matrix for that? Now, if you look at the u matrix or u vector and find out where the I hat would land on the u vector, we use a beautiful argument of symmetry by showing that it would be exactly the same as projecting u onto I hat, which would be u of x. Using the same logic for the j hat, we get u of y as the second component of the matrix, giving us the linear transformation u of x, u of y, for projecting some random arbitrary vector onto u. So the projection length of projecting v onto some vector u is given by u of x times v of x plus u of y times v of y. This projection length can also be written as u mod v mod times cos theta. This algebraic structure is called the dot product. Now, going back to the directional derivative, we can recognize this same structure here also. Using the projection length formulation, we get this. Now, clearly, the directional derivative will be maximized when cos theta equals 1, meaning the u vector and the gradient point in the same direction, thus giving us the fact that the gradient is the direction of steepest ascent. This entire derivation uses the simple fact of symmetry of mutual projection and the fact that it comes from linearity and orthogonality of these axes.